Yeah, that's nice to hear. But you mentioned that you're not American. Are you Swiss or from Canada? Because you did your degree in Canada, right?
I am
In
Canadian.
Waterloo, if I remember.
Yep. Yep. So I am Canadian. You would think that American and Canadian culture is quite similar. You're shaking your head. You know. The hardest thing is the whole self-promotion and showing what you do. I've been so much more on like, look at what my students do, look at what the lab's doing overall, and look how cool that is versus the whole I did this and I did that. I'm still struggling with that aspect of what's not expected in American culture, but very common. So that's been a huge culture change for me.
Yes, and that's also somehow represented in your choose of your selection of the name for your lab, right? Because a lot of professors name their labs after their own surnames or names, right? But your lab is Smarty Lab.
My name is embedded in there, but I never actually say it.
Okay,
So
okay. How is
it
it?
is
How is it? How is it?
it's the Sychterz modular adaptive resilience a transformable infrastructure.
I see.
So it's in there, but I never actually say it. So it's kind of it
Oh,
straddles
that's a
both
nice.
worlds. Yeah.
That's a nice way to you know to confront that different in cultures that you mentioned. That's nice.
Yeah. But you mentioned about my students. They actually really enjoyed. They all wanted coffee mugs with like their personalized name on it, so that they could have tea or coffee. But it was kind of the lab logo.
Oh,
So they actually made an initiative to get coffee cups all matching, and also like mouse pads for themselves. So uh, they can have this like logo and this Smarty Lab on it. So I thought that was very
well,
cute.
that's a very nice detail because it also creates this bond between the lab members, right?
With Ian, we had a very like the lab had a very tight bond, and I realized how important that was for me for all of us to get through our PhD. So
Yeah,
I
it's not
wanted to
always
continue.
easy to it's not always easy to foster that culture though, right? So it's a
Yeah,
nice detail that you have there.
thanks.
So thank you very much for accepting. I think we have the numbers have stabilized now, so maybe we can start with the research seminar.
Hmm.
So I'm very happy to have you in our structures research seminars on Sychterz. I hope I'm pronouncing it correctly.
No, that's great.
So you hold a PhD from EPFL and you are now um, at the University of Illinois in Urbana-Champaign as an assistant professor leading the Smarty Lab, right? So please share your screen.
All right. Well, thank you everyone for your afternoon. It's morning here in Illinois, but great. Really glad to be here. So today I'll be talking about adaptive and deployable lightweight infrastructure. And this is my group, Smarty Lab. I am Canadian by background, so when I was coming up with a name for the lab, this is what I was thinking of. This is the Smarties. In the U.S., it's a very different candy, and no one likes it. So I have to explain what Smarties actually are on from my side, and at least in for you guys as well in the UK, it's the same thing. So at least there's a cultural thing there that I don't know. I have yet to have a bowl of Smarties in the middle of the lab, but that's kind of a plan I had for Halloween coming up actually. So first we'll start off with an introduction to tensegrity structures. Why also they're so interesting for actuation. They're coupled and they're deployable. So they're really great candidates to study how to control these structures and look at adaptation, so small changes within the structure to address certain needs. So tensegrity structures are pin-jointed structures. They're self-stressed, and because of those changes, they are geometrically nonlinear. They're all made of struts and cable. So on the left-hand side here, you'll see Buckminster Fuller with his traditional tensegrity structure. In the center is maybe something it's tensegrity-ish, the self-balancing chair that you may have seen on Reddit or some of the internet sites because people are really fascinated about this right now, and I'm quite interested in the fact that my research is actually making it to mainstream media in a way. And on the right-hand side is the top view of the Tensegrity structure that I worked on at EPFL. That's actually 12. Sorry, I can speak metric with you guys. 4 meters long and in the lab. Taking a closer look at this, it was an adaptive deployable Tensegrity structure. It is robotic, so it is a pentagonal module, and there are 4 modules in this view. 2 halves that deploy from each of those left and right sides. There are 10 motors in total. Those are kind of those blue things you see, 5 on each side. So all of those can be independently controlled, and they wind and unwind cable that you see with that dot dash line from the support all the way to the midspan. So it controls the length of each half. At the center, the 2 halves connect with electromagnets, so it's completely hands-free. And the springs along the peripheral aid with the actual deployment process because the shape of it, in fact, dilates and gets larger as it folds. So this is a view from above. It's 4 meters long in total, about 1.5 meters wide and tall. So it's tubular. The idea is that it was going to be a pedestrian bridge structure with the tube being the outer component of the pedestrian bridge. This is at a quarter scale, so only a toddler could really walk through, and we didn't have a deck on it for the reason that we didn't want people to walk on it in the lab during testing. We're just looking at the general structural system. And the whole thing weighed about 200 kilograms. So in terms of the actual simulations, originally it was just assumed to be frictionless. The cables that pass over many points over the structure, in fact, they do have friction, and that really changed how well we could control the structure. So using dynamic relaxation, which is a form-finding method, I was incorporating sliding friction, in fact. So how many points does it touch? What is the angle at which the cable forms? So how much friction are we actually experiencing? So you see that that orange arrow shows the effect of friction versus no friction, where the black structure is the one that has a simulation with friction. And you would see that without accounting for friction, maybe the structure could connect in the middle, but in reality it wouldn't. So we're trying to get closer to the ideal solution. Along with the simulations, we also had to look at how to program better controls. So starting with just the controls that worked in the lab to make the 2 parts fit together. The structure had its own intricacies because of manufacturing, so it's actually the deployment was not entirely repeatable, slightly different each time. We would use optical tracking to measure where nodes are versus where they would be in the simulation. Using essentially a correction factor, we could then update the commands for the cables. So tell the motors to unwind, instead of 5 centimeters, we could unwind 5.15 centimeters so that we could get a smoother deployment that actually connects very well. The whole point was to make it smooth and efficient command to move the structure. That means that we could speed it up in the future and that we're not looking at fatigue issues. So the blue line that you see here is without any type of feedback cycle that I just explained. It's a little bit rough and we have some bumps and hiccups along the way, and it takes a lot longer. If we do 4 feedback cycles, so we check it, we readjust the commands, and we go again. It's shorter, kind of lumpy. It's not doing so great, but it's a little better. In the case of this structure, but it's not true for all of them, every structure would have its own story. 20 feedback cycles meant a much smoother deployment, a much shorter actuation time, and we didn't have those hiccups that you saw there. With a different structure, it would be a different number of feedback cycles. This was just what it worked for this one. Beyond 20 was just extra computation time that didn't benefit the shape. Now, the Tensegrity structure has cables and bars that can easily get self-locking. So we tried to avoid that using the rapidly exploring random tree command. So that's a searching algorithm. So you can see here on the left-hand side, there's 2 paths actually. So in fact, the RRT connect is when you have a starting and an end node, and you kind of search starting at those two nodes until you have a connected path between. So that would be the black and the gray moving towards each other until they find a successful connection. Now, the commands to find that search was actually to compare all of the different nodal positions in the Tensegrity structure and to ensure that none of the bars were colliding with each other or passing through each other. So this was checked at every stage of deployment. But that ensured that there was no overstress and no element collision. So this is a video of putting that all together. So the feedback cycles, the RRT star connect, which is what I combined different methods to optimize for this structure, was used when the structure was more folded, when locking and binding of cables and bars was a bigger concern. When things are a little bit more opened up, then you don't need the heavy computation. You can just let it go evenly and nice and smooth. And then the feedback cycles were really useful for searching at the end so that the two nodes that match up can actually connect using those electromagnets. And then the self-stress at the end was to ensure that the stresses in the cables were as evenly distributed as possible, as in it would be ready for in-service if it were to be a pedestrian bridge. Now, another aspect that I was really interested in and coming from Waterloo was I was really into structural dynamics and how do we understand output only signal from a structure. So using the second order blind identification called SOBI, it's kind of like trying to parse out the dinner party scenario where you hear a lot of people talking, but you're trying to listen for only one particular voice. So the one that's right next to you, or if you want to try and listen to someone who's further away. So using second order autocorrelation and cross correlation statistics, trying to separate out the natural frequencies, which is also based on the number of sensors that you have installed on your structure. So you can have your frequency and also your mode shape. So this was extremely useful for my work at Waterloo when we were testing the vibration characteristics of aluminum pedestrian bridges. And this was in partnership with Madi Group out of Montreal, who was looking at the maximum length that we could make safely with their extruded aluminum structures. It's kind of a modular two order length of bridge that they have planned. And so we did walking tests, crowds of people, and so we used those autocorrelation, cross-correlation methods in order to parse out the natural frequencies of these bridges, including a 70-foot span. And the image is extremely distorted because very tight space, and about 21 meters in the lab. So it was a very impressive structure to be working on. And so we found that the methods used to parse out the measurements really correlated well with the finite element models, as you can see for the 2 bay, which is the short one, 8 bay, which is the mid-size bridge, and then the 14 bay, which is that 70-foot bridge. The finite element models and the measured frequencies really matched up well. We're like, okay, great. It's a truss bridge. It's a little bit more predictable. So I was really interested in applying this to the Tensegrity structure because there's so much more going on with that one. So we actually used it for the purpose of damage detection and location. So first of all, detection is whether something is damaged or not. So just a true false. Examining 4 different cables, which were easier to test than, let's say, the struts. That one I did after I received PhD in hand because replacing a strut was potentially more damaging. So cables were really easy to damage and replace using an electromagnet that would click and unclick, basically. And then damage location, much more complex because of your multiple load path situation. And that was using an exclusionary type principle called arrow domain model falsification that I'll go over. So using that SOBI method that I mentioned previously, this is just kind of a snapshot of the first 3 natural frequencies of the Tensegrity bridge. First showing healthy, so as in no cable was damaged. And then once the structural frequencies extracted from the structure once a cable was broken. If that precision, meaning kind of a tolerance, was less than the change between damaged and healthy, we could say that damage was detected. If that precision was too high, like for example, the changes when it was damaged were not enough, then we'd say that there wasn't a significant change. We'd say the structure was not damaged. And we check those 4 locations. So if some passed and some failed, that's why there's a possible, or if all of the damage frequencies changed the structural natural frequency enough, we would say, yes, the structure has been damaged. As for location of the damaged elements, using that idea of generating a bunch of different models simulation-wise, having our primary factors that we know are important to the structure, each with their statistical importance. So we have the measurement and modeling uncertainty. Then we combine all those factors together and we try and compare all those scenarios to our actual measurements. So we try and see which of our models explains the measurements, and that will reduce will cut out the models that don't make sense. So we're not looking for one optimal solution, but we're looking for a small field of solutions, which is more useful when an engineer goes to site and we say, okay, a couple of these elements look uncertain. So look at 4 of these elements, and one of them will definitely be the one that's broken. Versus we send the engineer to site and we say this one element is broken, but our algorithm was a bit off, or it was hard to pin down, and it actually isn't the one that's been broken. So then the engineer just comes back and says, well, it wasn't that one. I don't know where it is. So we found that this method was useful for very practical purposes. So this gave us a bit of a region of which to inspect. So when comparing the measurements to the simulations, we kind of a swath of effect. And when it came to cable elements that we're expecting, and knowing that the cable was damaged, that swath is actually quite tight. So we would see that if we sent the engineer this map, for example, it's a very clear on where that damage has occurred, even though it's a complex system that loads low pass through a range, and the whole shape deforms in the process. That's great, but it does take some time. So what happens if we run the simulation a bunch and use case-based reasoning to make the process shorter in the future? So you see that the first section there, section A, is when everything was being learned. We damaged a bunch of cables. We compare it to simulation. Each of the run times take quite a long time. But as we then run more cable break situations, but then draw off of previous experiences, all of a sudden the runtime starts to decrease dramatically until it plateaus well into the about 200 iterations. So this is where learning, and now I'm looking more into machine learning, has been super useful. Based on my work on aluminum for not Montreal, that's where I'm originally from the work in Waterloo and my Tensegrity work during my PhD, I was really interested in championing the both. So we have an aluminum Tensegrity canopy that's in the process of being built. So this is a simulation of where it will go. I bike to work, so we don't have a cover for snow or rain over bicycles right now next to our civil engineering building, and that's what I'd really love to see. So this is a plate-based Tensegrity structure that is based off of designed by Falk that we're in the process of building. One of my students is really doing a great job with this. You'll see these are some of her renderings of the plate-based Tensegrity structure. Each of the plates is about, and this is more in the imperial units, that it's 1 foot by 1 foot plates, easy to assemble, modular. So we're in the process of making the roof itself. a 6-foot by 4-foot aluminum canopy currently, and there's a bar that's continuous from top to bottom that is 2 feet long, all made out of aluminum. We have the kind of tab slots that connect all the cables together at the top and the bottom of the bars. So using ASC 7 load cases, we're looking at wind, we're looking at dead loads, and so we have a bit of a curvature because the university was interested in a higher ceiling height at the front of the bike parking canopy, and it also gave us an opportunity to look at some curvature of the roof. So looking at some deflections, obviously there is some, but we're in really good tolerances right now. And obviously with mechanical couplings, we can tune that up as well as we're manufacturing it. But we're all looking good in terms of the plate thicknesses and the bar strengths, and also our stainless steel cables that we'll be installing on this on the modular structures. So the problem with some of the Tensegrity structures, and the canopy is great because it's not moving, so at least the university gave us permission to build that on campus. But with the moving Tensegrity bridge, the challenge is that no one's actually seen this in real life. So one of the really exciting things I got to work on was building this in VR, in virtual reality, so that we can show people what it could really look like if you would walk through the structure. So with help from the Supercomputing Center at Illinois, I got to work on this really great project where we could even, disconnect the structure, reconnect it. The cables are actually continuous, just like the real structure. And there's a deck that comes in later that you can walk across. We made the deck glass so that you could look down. Hopefully you guys aren't afraid of heights, but there are railings so that you don't fall off. But it's a really fun experience and an easy way to show other engineers, people who are interested in maybe building these things, or architects, of how it feels. So this is something that was hard to convince people with just 2D drawings, for example. So I'll just put it further back where you have on the bridge itself, there's the actual deck. And we have our stick to actually, we can interact with the structure, you can actually move it, which is quite exciting. So we even have a way of measuring displacements in real time. This was actually really useful, so you can compare our simulation to the actual measurements I got in the lab. So from the Tensegrity side, learned that retrieval and adaptation increases the speed of determining the control commands, which has really been something that we can take away for the future projects, and that these advanced computing algorithms being RRT star connect and SOBI have been really great at improving the efficiency for determining complex deployment challenges like blocking and control. The aluminum increases the constructability of the modular Tensegrity structures. It's so much lighter, so much easier to work with. Yes, aluminum is a bit more, but also is corrosion resistant. And the Tensegrity grid has successfully been able to passively adapt to load, so it can slightly flex without stressing out. So the other half that I'm going to talk to you about is actually about origami structures. And obviously origami structure uncut sheets consisting of valley and mountain folds. Kirigami is the one that are cut pieces of paper. They can be developable from a flat sheet and can exhibit rigid foldability. So what you'll see here on the the left-hand side is more artistic origami, like a dragon, or kind of scientifically what we use as a first basis is the Mura-Ori, which is a very simple pattern that is flat foldable, rigid, but can also be, we can also look at non-rigid behavior of it. So obviously looking into actuation, which is kind of what I was interested in during my PhD. When I went to Michigan, I was like, great, how do we actuate origami so we can move things repeatedly and not necessarily just by hand, but if we're dealing with larger structures. So in the longitudinal direction, looking at all the realistic actuators from end to end where we could put them, and what their effects are. So the actuators are those red bars that you see, and then we'd measure the nodal displacement in the longitudinal direction. And how to actually model origami. So I was using dynamic relaxation again. There are other methods. However, dynamic relaxation is fast and doesn't require the inversion of the stiffness matrix. So when you have large displacement structures, it's really handy. So they needed an extra component, which is that thing in blue, which is actually calculating the folding and bending energy. And that's because the actual fold of an origami structure is not just a free hinge, but it has resistance. So that was the new component that we developed in our paper in 2021 about origami Murori structures. And so it's the process of dynamic relaxation, basically original configuration, having a nodal velocity that causes nodal displacements, calculating your energy that produces some residual forces until those disperse. It's an iterative process until the final shape has been reached. So essentially shaking a structure until it finally settles into its final shape. In terms of the dynamic relaxation, so you look at the different folds. You have one between panels, and then actually within the panel itself. If you're looking at non-rigid movement of the panels, those panels can bend and flex. So it's just taking the vectors and taking the normals to those so that we can always compute the angle for each step of the panels relative to each other, or within the panel, the actual square, how much it's flexing. So these are the two folds. So KF is the stiffness of the fold, and KB is the stiffness of the bending of within the panel. So in terms of looking at those locations of actuators, all of a sudden, when you have non-rigid foldability, you see that where you put your actuators is very important. So if you have one actuator, as in you have less money for it or it's just hard to install, the best case, as you can see here, it folds nice and evenly. If you have three but put them in the worst location, you put them all just in one module, it starts to really crush the one. You can also space out the actuator so that everything is more evenly distributed. So location matters versus kind of the ideal location, ideal situation of actuators everywhere, but that's much more of an expensive option that we don't necessarily want to explore. So this was also looking at bending, and big thing was curling, which is obviously panel bending that's not rigid for continuous cables. So this was the first studies I was doing during the pandemic. So this is a rig that we set up with a camera for tracking with that black and white grid. So this was kind of our first medium-sized proof of concept with paper, but we've definitely moved on to 3D printed rubber hinges and harder plastic panels. But then comparing dynamic relaxation to our actual measurements, we're looking at the difference between the two, and we saw that dynamic relaxation was pretty strong in how it characterized the movement of the origami structure. So that was really exciting. And we've moved on to some other really cool origami structures, including bio-inspired origami. Pill bugs or roly-polies, depending on how you see it, are really interesting. They can roll up when they get stimulated, and they kind of like an armadillo. If you've ever seen, not sure where else are armadillos, but in the southern U.S., they have armadillos as well. This idea of having an external shell that can roll up into a ball, and looking at actuation on top of that from the inside to actually, like muscles of a bug, basically, to initiate that curl. I was more focused on the actual shell for the moment, though. So applications, it can be really useful for temporary shell structures, for pop-up shelters, for example, something going from completely flat, easy to transport, into something that's a kind of a semicircular shape. It can be tunable as well with that idea of the motor or the control underneath. And so on the left-hand side, you see the 3D printed structure is just kind of a 30 centimeter model that we have. The clear parts are hinges or rubber, and then yellow is hard plastic. And then you see here the same rig before controlling the curvature of the structure. So we wanted to look at the dynamics of this So using Sophistic is a German software really great for dynamics. We're looking at the frequency of the structure. Obviously, it's not great at actually looking at the dynamics through different throughout the deployment process. So it's more just spot checking the shape of the structure throughout the deployment process, and those coordinates are from dynamic relaxation. So what we're looking at is a change in stiffness of the structure from when it's unrolled, as you can see the bug on the left-hand side of the graph. And then, sorry, it's stiffer up at when it's unrolled, and then it's a lower stiffness when it's all rolled up. So we're trying to use this now as then structural components where we may need to mitigate vibrations, for example, which is super interesting. As I mentioned previously, we used a Stratasys 3D printer, which is a resin-based printer. So you don't have as much of the striations and the issue of bonding between layers for the origami. And so this is a yellow plastic, so you have about an FY of 65 MPa, and the folds are much softer at about 2.5 MPa. We load it with loads off the pulleys, as you can see there. And we're actually in the process of using a camera from above for machine vision to track the deployment and the deformation of these structures, which is actually really exciting. So preliminary stuff here. This is actually work by one of my students developing the code to calculate the differences in the at least longitudinal and some lateral displacement of the origami structure throughout the deployment process. And so this is just using a Q-tip, but we're using smaller components to track now and looking at the more refined way of measuring, so different cameras, and then also a lot more tests to see how these structures behave. So this will be compared to the dynamic relaxation model of this structure that we also built. So comparing it for the ruled origami structure, dynamic relaxation versus the image tracking so far, we're getting a pretty close results. So we're really excited about that. But we just need to do some more tests and confirm, refine, that kind of thing. So we're really, really excited about that. That work is going to be coming out quite soon. And then as a wrapping up on the origami side, looking at that, the big thing that we take away is that dynamic relaxation is super useful for origami structures, especially when we're looking at actuation. And the new module that was built for dynamic relaxation is super useful for not only mirror ori, but for other more intricate shapes or less common shapes, I would say. And so it can also be used to calculate the energy from those folding and bending stiffnesses, where we can actually either detect that damage is going to occur, or that's going to be a good location to observe when damage occurs. So kind of coming back to that damage location and detection from the tensegrity structure. And as mentioned before, applications so far that we've identified: building components, lighting, shading, that kind of thing. Architecturally, this could be, we're looking into exactly how to implement these. Emergency pop-up shelters has been a big one, and then vibration mitigation because of the change in stiffness of the structure. So been a whirlwind of stuff. My team, I am so glad to have my team. This is the whole crew now. So Angshuman more on the origami pillbug side. Sagnik is on the tensegrity work and architect and materials. Heather is working on the aluminum tensegrity structure, and Juan is actually on VR for education, and Matt and Kaylee are working on actually deployable underground structures, which I didn't even get to in this presentation, but really exciting stuff going on. With that, I have some of my funding and collaborators. And at this point, I'll mention that I have an Instagram for my lab because we do some quite visual stuff. We also have a website if you want to, if you're interested at all. There's a QR code there you can scan. But at this point, I'm open to take any questions, and thank you for your attention.
Thank you very much. Thank you very much. Fascinating, Anne. Does anyone have any question? you can either, it's probably better if you raise your hand and then unmute yourself to ask the question, or if you don't have that facility, you can also type it in the comment section. Yeah. I don't see, while they prepare the questions. Now, I was seeing your video of the Tensegrity structure that you built at EPFL, right?
Mm-hmm.
And it's a relatively large structure. In that case, you are also measuring displacements, right? So your control is based on deformations.
Correct. Yes. So we actually had optical tracking cameras at the supports measuring different specific nodes. So when it came to the connection, then it was the 5 nodes on the end on each side. So we had 10 points that we were tracking to ensure that we had connection.
Those are the ones that are going to be connected at the end. Yeah.
Exactly.
And at some point, we see the structure sort of drifting, especially when it gets very close, right?
Yes.
And then comes back. Why is that?
So, and that's one thing I didn't happen to mention at that time, but in aerospace, tensegrity structures are very common, and they do not have the same experiences with gravity that we do on Earth. So we actually had 2 cantilevers that we had to connect that were deflecting downwards because of self-weight. So we couldn't unfortunately connect one node at a time. We couldn't connect all 5 nodes simultaneously. We had to connect one node at a time because the top actually sagged and that node was connecting first. Once that was connected, we could then stress that cable and use it to kind of suck the other side back in. So it was no matter what actuation scheme we had, that was the mechanic that we had to do because of self-weight.
Well, that's great. So that's basically designed in, right? So that's the way you designed it to behave to connect it.
Well, yeah, you can't push a tension only member, right? So if it's slack on the bottom, there's nothing you can do about it. So you can only extend the top. So yeah.
Well, there's a question in the chat. It says, "Thank you very much for your insights. Could you please explain why you define damage as a change in frequency? Does change in frequency mean the bars change their configuration?"
I'm trying to see where is the show conversation. There we go. Okay. Yeah, great question. So I dealt a lot with structural analysis when it comes to dynamics previously, and when it came to displacements, it's less precise in a way that, yes, things move around so much. It's a deformable structure. If it were a truss, we could definitely measure displacements and say that that leads to damage. However, because this is a deformable system, it could still move in a way that in other structures that would indicate damage, but in this one, it's just shifting stable, intact shapes. So when it came to damage, if you had a snap of a cable, that is going to induce a dynamic property to the structure, and that's why I was leaning towards dynamics, because a rupture is going to cause an impulse load.
And then we have another comment. It says, "Thank you for such a fascinating talk. Did you experiment with using different form finding methods? And if you did, what variation did you see that caused you to use DR?"
Yeah, so I would say my work was actually in the lineage of tensegrity work at EPFL, and different methods were actually utilized in the past for especially more adaptive tensegrity structures, so smaller shape changes, looking at the force density methods, for example. And so those I had tinkered around with at the beginning, but dynamic relaxation happened to be the one that end up being also the fastest in this case as well. So like there's more so I did a quicker research on, sorry, my cat's here. there was some preliminary work at the beginning of the PhD that made me focus into DR, but it's not that I revisited each time just because it was the core of so many algorithms, search functions. It had to be quick, and giving the nodal displacements and the forces was just really useful. So I understand there are lots of other different methods that can be utilized too.
Maybe we have another question. But in the meantime, also, yeah, thank you, says Pasi. One always asks this question about the lab conditions versus the operational conditions, right? So you've worked quite a lot on control, right? And I don't know how sensitive would be that to the the noise that we have in normal operational conditions.
So a lot of my work has to do with uncertainty quantification. So where does simulation and theory or in lab conditions, where do they differ? And then there's also where lab conditions differ from real life. And so now I'm getting more of the opportunity to put stuff in real life, but I will say that the structure that was in the lab was actually at EPFL, was testing multiple aspects of control and tensegrity structures all at once. So rather than building a few tensegrity structures that address only one topic each, it smashed everything together. So the structure itself that was in the lab was not viable as a piece of infrastructure to be put directly into practice. So there would be fewer aspects that could have uncertainty. So whether it's a static connected structure and only adaptive, that's something that could more likely be put into practice. And so there's just a certain amount of practicality of what aspects do you keep from the lab and which one do you actually implement from the lab. And yes, so noise, wind, for example, depends on what kind of sensors you have, where you put them. I'm dealing with a project with the Illinois Department of Transportation. So where do you put sensors on a bridge for vandalism purposes, that you're not getting excess noise or conflating between different sensors. So yeah, that's definitely an aspect that I've been interested in for sure and get to do now.
There is another question in the chat. Thank you for your answer. There's another question in the chat that says, how did you implement dynamic relaxation? Did you write your own scripts or did you use specific software?
We wrote our own scripts. So when it comes to the machine vision, dynamic relaxation, all of that is our own scripts. So that's why building in this this module for origami stiffness of hinges was really handy, because it was our own basic calculation. So the only thing we use as a package software was for dynamics. Even though dynamic relaxation has the word dynamic in it, it is a static solution. So if we wanted to find out the vibration characteristics of the structure on a more system level, we used that's the only package software that we used.
And the tools that you use, probably they are interested also in. You use, I guess, I don't know, Python, MATLAB, or.
We use MATLAB. I've been meaning to transition into Python. It's just with so many other the search algorithms and stuff being built in MATLAB, it would be a big transition over. So it's something that's on the to-do list. But when things work, it's kind of it's hard. It's a hard moving boulder, right? But it's something I'm really interested in doing for a long-term thing. It also depends. Like LabVIEW, for example, had a great plugin for MATLAB, which is if we were to try and compare measurements to simulation, having that plugin in LabVIEW was super useful, and it wasn't necessarily the same for Python, so that made us put that on hold.
I think that's the main weakness of Python, right? The LabVIEW aspect of things. It's really where.
Yeah.
But yeah, fascinating. Thank you very much. It was a brilliant talk, and I'm just fascinated. How do you get your idea? I mean, where do you get your ideas from? What's your inspiration process?
So the actual design of the structure, the conceptual stuff, I mean, to build that big structure within 4 years would have been too much. Like that, I didn't actually make the conceptual side. So that was started from another PhD. So the actual topology is thanks to René Motreau out of the University of Montpellier. He was collaborating with Professor Smith. And so that's how they came up with this topology. And then they thought, well, this could be a pedestrian bridge. But then with the lab of Professor Smith, he was the one who had the space to build kind of a scaled model of that. So I didn't come up with the shape. The origami thing, that was something, the pill bug, that's actually because I saw one day and liked the idea that it rolled up. And I'm like, that's cool. And there are some really interesting people to collaborate with at, for example, at Illinois that are in bio-inspired entomology, for example, that really like to work with people in robotics and civil engineering. So I said, I have this idea. This is cool. I'm not sure if it works. So that's who we've been playing around with this idea. As for the canopy, like I mentioned, Andreas Falk is actually the designer of the plate tensegrity idea, but then I like to make the structures large scale and usable, but I would say I'm not the architect of it. So one of my students actually is Kaylee, is a architect. And already the way she's challenged our group of why not this shape? Why not parametrize this or do this? It has opened up our minds, and there are so many new options now. So I'll say I'm not the artist, but I just like to make it different materials, make it large structure, different applications. So yeah, so I do need that artistic push.
Great, fascinating. Thank you very much, Anne. Thank you very much for the presentation. It's truly nice to see your work.
Yeah. Thank you. There's another question actually. Deployable tensegrity could have.
Yeah. Do you think deployable tensegrity structures could have implementations in vertical structures? Following vertical your research.
So there are boom type deployables that like boom mass, for example, and is that, I'm not sure if that vertical structures in like buildings, or I'd say that buildings itself would not benefit directly from tensegrity structures because it is a compliant structure by nature, but building components like facades on top of vertical structures, definitely. You can even see kind of tangential work at University of Stuttgart where they have that adaptive structure and they have, things on the facade. So that's kind of in the same vein of what I've actually tinkered around with that idea as well. That aluminum canopy could also be put on its side, and having that adaptive shape could be really interesting. So not the actual structure itself, but components of it, yes.
Thanks a lot. Yes. Thank you very much. Thank you very much. Yeah, great. Thank you again, says Shajan. Thank you very much, Anne. Thank you very much for your presentation once more, and thank you for answering our questions. So,
absolutely. If you have any other further questions, anyone, please feel free to reach out. Thank you so much for the invitation. I had it actually, in fact, in 2020, had 2 conferences in the UK to attend, and unfortunately those both changed, but I hope to make it out to the other side of the Atlantic whenever it's safe. So
just drop us a note, and yeah, we
and likewise for Illinois. I know we're not really a destination location, but we're a good transition into Chicago if you ever need to go. It is beautiful this time of year. I have to admit, it's very pretty, and the leaves are changing and that sort of thing. But it's not Chicago. So, but you're still welcome to come.
Great, perfect. Thank you very much.